So I think most of you know Jerry, have seen Jerry present before, have maybe had Jerry out troubleshooting issues at your hatchery. Jerry has been with Jamesway since 1996. He came to us after a career in hatchery management and hatchery and broiler operations. And before that, a poultry science degree. And as many of you know, Jerry has been our resident expert for quite some time here on all things incubation. So we are very excited to have you here today to go over that hot topic in the industry, metabolic heat. So with that being said, I think I'll go ahead and put up Jerry's presentation and we'll get started. Here you go, Jerry.
Okay, thanks everyone for attending the webinar. It's indeed an honor and a privilege to present this to you. And like Victoria said, this is a hot subject. Heat is a hot subject. So we're going to be talking about embryonic heat, the management of embryonic heat, sort of from a practical standpoint, not so much from the scientific part of it, but just a practical standpoint, what you can do at your hatchery to better manage the embryonic heat that's generated by the embryos in today's modern poultry industry. What is required for incubation? The four factors that we talk about is heat, humidity, airflow, and turning. As we take a look at each one of these separately, the heat is commonly referred to as the driving force that establishes and maintains and controls the embryonic development. So heat is a major, like Tori said, heat is a major factor or major thing in incubation that we must manage properly. Humidity, a simple definition of humidity's function is to control moisture loss. Of course, in some of our machines or in machines, when we use spray, it also has a cooling effect, but the primary function of humidity in incubation is to control the moisture loss. The airflow creates the correct air movement through the egg pack to obtain, maintain, and distribute the correct air temp and humidity to achieve and control the embryo temperature. The turning function is to properly orientate the embryo during the early stages of development. After 12, 14 days, the turning then is not really needed. And in our single stage machine, we actually stop turning at day 14. The process of incubation, there's three control factors in incubation: the temperature, the humidity, and the damper. There's one established factor, and that's the airflow. The airflow is established by the fans and their function. One program factor is the turning. So as we look at that in perspective, the process of incubation involves these five things, basically: the temperature, the humidity, the damper, which controls the oxygen and the CO2, and the airflow and the turning. These five things are what's involved in the process of the incubation. Embryonic development. The fertilized egg transitions into the embryo that produces the embryonic heat in the incubator. In other words, we start out with a fertilized egg or a fertile egg, and as it matures and as it grows and as it develops, it starts producing the embryonic heat in the incubator. Embryonic development is a progressive change in the molecular structure involved metabolism, growth, and heat. The natural byproduct of embryonic development is heat and CO2. As long as the embryo is developing, it's producing heat, and CO2. The heat, that's what we're going to be talking about today. Again, the heat is the driving force that establishes, maintains, and controls the embryonic development. In the early stages of development, heat has to be supplemented or heat has to be supplied in order to get the embryo off to the proper start. It has to be heat has to be supplemented or supplied to the embryo, and in the mid and latter stages of the embryo begins to produce the heat on toward the 10th, 11th, and 12th day. I've got some pictures I'll show you in a minute about when that actually happens. Proper heat is of absolute importance throughout in establishing the correct incubation temperature. Proper heat is absolutely important in establishing the correct incubation temperature. Proper heat allows for proper and precise embryonic development. Proper heat produces the quality of chick that yields the results that affords the profitability in today's very competitive poultry industry. So the quality of the chick and that we produce and the heat that's involved in this is very important, that we manage this embryonic heat properly in order to achieve the chick quality that yields the results out in the field for the companies. Managing embryonic heat, when you look at it in perspective, in the old multi-stage machine, in the first two positions, we need heat, CO2, and humidity high. In the neutral stage, or in the second stage, we just need a blend or a mix of heat, air, and humidity. It's just an average going across the embryos to or the eggs to maintain the proper heat for the embryo to continue or maintain its development. In the latter stages, we need cooling, oxygen, and low humidity to achieve the characteristics there. And in the multi-stage machine, this is achieved properly through the airflow. Too much heat at the beginning accelerates the hatch. Not enough heat at the beginning depresses the hatch. Too much heat at the end can actually slow metabolism. Not enough heat at the end can depresses the hatch. But in other words, if the embryo is overheated in the latter stages, it can actually slow the metabolism or growth of the embryo because Mother Nature says, I'm too hot, and it depresses or falls back on the metabolism. Our focus today is the management of embryonic heat as a primary responsibility to incubation. So as we begin to talk about now the actual management, and we need to understand or understanding that it is a primary requirement or responsibility to incubation is the proper management of the embryonic heat in the incubator. 3 things to consider in managing embryonic heat. The air temperature required to maintain and control the actual embryo temperature. The outside controls the inside. The air temperature on the outside controls, regulates, maintains the embryo temperature on the inside of the egg. So air temperature is the control. Therefore, you got to have the correct air temperature in order to achieve proper incubation. This graph here you'll see again, but it's not very, you can't see the numbers very well in this small slide here. But what it's showing here is that the temperature starts out high and finishes low on this slope or on this type of curve. we usually start incubation at somewhere around 100.4 and finish it somewhere around 97 in the incubator. Another thing to consider is embryonic heat produced by the embryo. You know, the embryo, as it transitions and as it matures and as it develops, it starts producing heat. So the reverse curve shows that as the embryo starts, it's no heat generated, no heat produced, but as it gets older and as it gets past that 10th, 12th, 13th day, it begins to really accelerate and starts producing the heat that has to be properly controlled by the air temperature outside the egg. The actual embryo temperature, or what we refer to as the shell temperature, and it's a constant number. We usually started out about 100.4 down to about 100.2 to 100.1. And the air temperature, and I'll explain this a little bit later, the air temperature is what actually, the shell temperature is what we are monitoring, but it actually tells the air temperature what to do to maintain the correct shell temperature or the correct embryo temperature, okay? Another look at this, another way to look at this, the three things to consider in managing embryonic heat, is the embryonic heat produced. And if you look at that, I pull these different stages of development out of the slides that I had or the pictures that I had, and I started out with a 12-hour embryo, and there's no heat produced by just very, very, very little, 0.001 BTU of heat produced. At day 10, that number increases to like 0.10, and then at day 12, notice it doubles. It goes from 0.10 to 0.2, and then from day 12 to 14, it doubles again to 0.4, and then from 14 to day 16, the embryonic heat, or the heat produced by the embryo, is like 0.6, and then at the end or transfer somewhere around 0.68 to 0.7. So the embryonic heat produced is what we've got to at the beginning we have to supplement, at the end we have to, at the regulator, we have to control the air temperature to regulate or control the embryo temp. The air temperature that's required at these different stages, and I just pulled this out of the profile, is at the beginning we start out about 100.4, day 10 somewhere around 99.4, 99.5, 99.6. At day 12 it's down to about 98.6 to 98.8. At day 14 somewhere around 97.6 to maybe 98. And then 97.2, and then all the way down to 97, the air temperature. As the embryo starts producing this heat, then we need to control it. We need to regulate it to where the embryo is developing the way that it should be. The embryo temperature then becomes pretty, it's pretty constant. You know, if you start out at 100.4, you want to maintain that embryo temperature somewhere around that 100.4 all the way through the incubation process until about the day 17, 18, it might get on up a little warmer than the actual 100.4. But again, this is just another way of looking at it. The embryonic heat produced, the air temperature, and the embryo temperature. These three things are what we need to consider when we're managing the embryonic, when we talk about and when we discuss managing embryonic heat. What is embryonic heat? Three keys to understanding embryonic heat. The heat needed by the embryo to start and regulate its development during the first week. Second, the heat needed to control and maintain the embryo development during the second week. Third, the heat produced or generated by the embryo controlled by the air temp in the latter stages of development during the third week of maturity of the embryo. The embryonic heat correlates to the three thermal phases of incubation. Endothermic, the embryo needs heat supplied the first week. Second is the neutral stage, the embryo needs the correct air temperature or the correct temperature to maintain during the second week. Third is the exothermic stage, is when the embryo produces the heat, and this is commonly during the third week of embryonic development. During incubation, the developing embryo transitions through three distinctive temperature phases that we just mentioned. The thermal phases, phase 1 is endothermic, and we typically say that's the first 7 days. Phase 2 is the neutral stage, and that's usually from day 8 to 13, and then the third phase is the exothermic phase. And as we look at that in perspective, then we look at the three things we've already discussed, the air temperature, the embryo temperature, and we see how all this correlates. The shell temperature, 100.4, 100.2, and 100.1. You might ask why in phase 2 and 3 is the shell temperature not 100.4, because I told you that we need to try to maintain a constant embryo temperature, but the shell temperature as the embryo starts producing heat, inside the egg is typically in the phase 2, 1 to 2 tenths warmer than the actual air around the egg, and then in the phase 3 it's usually a 1 to 3 to maybe even 4 tenths warmer on the inside of the egg during the exothermic phase. So when we put the temperature to control the shell temperature, then we decrease the shell temperature to 100.2 to 100.1 in the second and third phase of incubation. The air temperature, then 100.4, and then it goes on down and goes down to the 97 like we showed in the previous slide. The function of the heat in the endothermic phase is to supplement. In other words, it supplements because the embryo has no means of producing heat itself, so it has to be supplemented. It has to be supplied. In the neutral stage, or the second phase, you have to just simply maintain the embryo at the temperature. So the air temperature will start, as you see up there, the air temperature starts decreasing, to maintain or to control the embryo temperature properly. And then at the third phase, it regulates or controls the amount of heat produced by the embryo. As the embryo starts producing heat, the air temperature around the egg controls the embryo development or the embryo inside and makes the embryonic development precise. Manage embryonic heat. Number 1, understand the source of the heat, supplemental at the start, and then the embryo. Second, understand the temperature, airflow, and humidity. What does the machine do? How does it take the temperature, the airflow, and the humidity? How's the machine function in that respect? Understand optimizing the parameters, the profile in the single stage or the set point in the multi-stage. And not only the set point in the multi-stage, but the set time and all of the things that's involved in the multi-stage incubation. Understand the cooling, the airflow, and CO2 control, and that becomes the concept and principle of incubation, is just the cooling, the airflow, and the CO2 control. Understand maintenance of the equipment. The maintenance program, very, very key in your success is the maintenance program. You know, I've been in hatcheries that was 30 years old that maybe looked like they was 10 years old. I've been in hatcheries that's 5 years old that looked like they was 30 years old. And all of that relates primarily to the maintenance program. And again, we need to understand how critical maintenance is in the performance and the efficiency of any incubation system. We need to also understand the characteristics of the egg pack, the needs and the requirements of today's developing embryos. And you know, as we get into a little bit further into this talk, then we'll see that the embryos are actually a little bit different than they used to be. The embryonic heat is the viable embryo inside the egg. We want that embryo. Remember, the natural byproduct of embryonic development is heat and CO2. So the embryo is what's going to become the heat producer, is the viable embryo inside that egg. Very important. The heat is supplemented at the start, as we've already discussed. The developing embryo then gives off heat. Not only does the developing embryo give off heat, but the developing embryo gives off CO2 and water. It begins to exchange water vapors through the pores of the egg and CO2, and again, it also consumes oxygen, which is very, very critical. Where does the oxygen come from? It comes from the ventilation system, comes from the outside. So oxygen is very critical in the latter stages of embryonic development. So again, as you look at this, the viable embryo inside the machine, we supply heat at the beginning. The embryo then begins to produce heat or give off heat. Not only does it give off heat, but it gives off CO2 and water. As long as it's alive, that's what it's doing. The developing embryo also begins to consume or to take in oxygen. And all this is done through the air exchange through the pores of the egg getting into the embryo. Embryonic heat production, this is from the past. This is a 39-year-old slide here. Made in 1979, and it showed that at 18 days, somewhere around 150 milliwatts, is that milliwatts of heat was generated by the embryos back in 39 years ago. From Dr. Garrison from the University of Alberta, she did a study for us a few 10 years ago, maybe? I think so. 9 or 10 years ago. And what her study showed that at peak, at 18 days, 200 milliwatt, some older flocks as much as 241 milliwatts. So quite an increase. Compare this, and it's a 33% to as much as a 60% increase in the heat produced by today's high yield breeds versus the breeds back in the early days. So again, very important. We have to manage this much more of the embryonic heat in our process today than we had to many years ago. Okay. Yeah. Okay, the high yield, according to Dr. Garrison, was again 250 milliwatts, and you see starts out at zero. In other words, at the beginning, the embryo does not produce heat, it gets on up about day 10. Look at the significance of day 10 at about 33, and then 44, 57, 82, 120, and then it just shoots straight up almost and gets to about 200 milliwatts. And again, that's just on an average size egg. It's not a young or an old egg, and her studies found that even the older, bigger eggs, some of them even as much as 241 milliwatts of heat generated. So again, quite a significant increase in the embryonic heat today. And again, this is 9-year-old data, and we haven't got it on anything, any of the most modern breeds. But again, this tells us that we do have the challenge of better management of the high yield heat production, because it's more of it produced. So we have to control it.
Do you think that if the study was redone today, that you would see even a further increase?
It's a definite change in the genetics. I don't know if it would increase or decrease, to be honest, because as we begin to try to fine tune profiles and we look at the major breeds, it is a difference, and I got a slide that shows a significant difference in two breeds.
Yeah.
One breed produces more heat, so it takes a lower temperature at the end than the other breed. So again, it is a probably yes.
Yeah.
Yeah. Okay. Now this is comparing to just comparing the two, and it's from 150 to 200 milliwatts. We're looking at about a 33% increase in the amount of heat produced. So again, it is significant. It is something that we need to consider. It's something we need to, as hatchery and as incubation people, we need to take this in consideration as we making our profiles or in multi-stage our set points and things. Factors affecting the amount of embryonic heat in the incubator. Fertility. I just took our large machine, the 129,024 egg machine, and I just plotted it to different fertilities, and notice there at 86% fertility, you got 79,000 BTUs of heat. At 98% fertility, which I have seen plots at 98% fertility at peak or at prime, is about 90,000, a little over 90,000 BTUs, which represents a pretty significant increase. So what I'm saying is, with the added heat production because of the high yield breed, and then the fertilities added into there, you can get quite a bit of heat load in an incubator very quick if you load it with all prime 98, 97% fertility eggs. Okay. So again, this is a factor that affects the amount of embryonic heat. Another thing is the physical age of the breeder flocks, young, prime, and old. The young flocks, the smaller eggs, is about I just plotted at 180, and the larger eggs at 220, and the prime eggs at 200. But according to the study that Galen did for us at the University of Alberta, she showed as much as 241 milliwatts. So again, I might have not got that exactly right on that, but again, the point is that the physical age of the breeder hen will affect the amount of heat in an incubator.
And that's also going to affect your placement of that flock in the incubator,
right?
Correct?
Your airflow is going to affect all of the things that you, in our single stage machine. Of course, we've got variable speed fans, and for smaller eggs, we might run our fan speed a little bit lower because, make a little bit more gentle airflow through them, because the egg pack is smaller, less resistant. So, and you get up in those large eggs, and you might have to run your fan speed on up to capacity, or something. 100%. But again, the two things we talked about so far that affects the amount is the fertility and then the physical age of the breeder hens. You know, because the size of the egg determines the size of the embryo. And the size of the embryo, the bigger, of course, the more it's going to produce. The third thing is breed comparison. This was taken from a prime age flock with high fertility. The shell temperature, we tried to maintain it somewhere around 100.2 all the way through. And again, look at the, this is the shell temperature. It's pretty constant. Both breeds was pretty constant. But look right here when it started separating. Breed B, the air temperature went all the way down to 95.3 to maintain and control the 100.2 shell temperature. The other breed, 7/10 difference, 96 to do the same thing.
Yeah.
So that was the same age breeder flocks, or same age of breeder flocks as all prime and very high fertility. Okay. So again, this is the three things that we've talked about is fertility, breed, physical age of the flock, and the breed comparison, and it is a difference. Okay. Controlling the embryonic heat. I went back to an old slide because I run into a situation a few weeks ago and I was asked at what point is it too hot and the embryos start dying?
Yep.
You know, in this particular machine, or this is an old slide, but it still tells us the zone of hatching potential. Start, mid, late, and end. This is still maybe not 100%, but it's still good information to know. When you get up in this 100, 101, 102, 103, 104, it begins to, it's lethal.
Is that air temperature or is that?
This is air. This is air temperature. All of this is the air temperature, not the embryo temperature. Okay. And it's also in C for y'all to see zone of injury, potential hatching, zone of disproportionate development, zone of suspended development. In other words, that's where you cool your eggs down to for storage, and then if you get them too cold, a zone of cold injury. But the main thing is this right here, the zone of potential hatching, and it's still what we use primarily today is the same thing that was used, and I don't know how old this slide is, but it's old.
It's old.
It's old. Okay. So as we take this information, and when we first started in this single stage stuff, we really didn't know much about profiling. But as we've got experience and began to learn a little bit more, the key to controlling embryonic heat in the single stage incubator is the profile, the air or the shell temperature. Okay. This is a typical, or this is not a typical, this is a profile that we actually use today. This is a pretty modern profile. Notice I've got it broke down in the endothermic. I call that the developmental part of the profile. At the beginning, when the embryo starts of its development, is cell division. Yeah. More heat, you know, faster, you know, so you can, that's the developmental part of the profile. Then we come down here to the second stage or to the neutral stage, and I call that my maintenance part of the profile. We just want to maintain what we've started. Right. And then the third phase, the exothermic phase, is the maturity part of the profile. That is where we finish the embryo, you know, it finishes off. Yeah. And the difference between a 14-day and an 18-day embryo is about 3 times bigger. You know, so it's a lot of development, a lot of growth happens during that period of time. Right. So again, this is a typical profile that we use. Temperature starts out starts out high. This is air temperature, and this is the shell temperature, or what we call a pilot egg. Okay, and I'm carrying it down to 100, and then back up to 100.1 here at the end, and this is the corresponding air temperature to maintain this.
Yeah.
Okay? Then humidity, and then we go low and CO2, and either we control our damper by CO2 or we control it by percentage. Okay. The shell temperature, I'm going to talk just a minute about the shell temperature. We use what we call the pilot egg. The pilot egg is a monitoring system that we have that nests in the egg pack in 3 locations, top, middle, and bottom. Each of these pilot eggs has 4 sensors, 4 infrared sensors that shoots the surface of the egg. Okay, each egg here shoots the surface of the egg. This data then is collected and averaged, and then it tells the machine what air temperature it needs to regulate and maintain that shell temperature. The location, like I said, is top, middle, and bottom. In a double ECU machine, we have 6 eggs, 3 in the back and 3 in the front. A single ECU machine, we have just 3 in the front. Usually try to locate these pilot eggs toward the center or toward the back of the front buggy to get them sort of, as far back in the egg pack as we can. And this is simply they're connected to the incubator by cables. Okay, so this has become a tool that I use a lot in establishing the profile and in determining differences between breeds and flock age and things like this. Is this pilot egg, or this surface temperature of the egg, or this shell temperature, and controlling the shell temperature to constant to know what air temperature is needed to properly incubate today's eggs. The profile that
There we go. Oh, no, it's missing. Where's the? Sorry. All right. There we go.
Okay, we got it now.
Little technical difficulty.
Okay, phase 1, I just took the profile and broke it down into endothermic phase, and then I wanted to show you the this is the shell temperature and the air temperature. Notice that it's pretty well, the shell and the air pretty follows down here. The embryo probably is starting to produce a little bit of heat, and it begins to separate a little bit the shell temperature from the air temperature, even in the endothermic phase. Then we go into the neutral phase, and we see the same. This is the shell temperature, and this is the air temperature. It begins to separate even more because the embryos start producing more heat, so the air temperature has to go down to maintain and to control and regulate the embryonic development. And then the exothermic phase, it even gets wider, but it's still maintaining that shell temperature with the air temperature. Okay?
Right.
So very, very important. And we look at it all together, and this is the graphs all put together, and you see the distinct pattern, the shell temperature and then the embryo temperature. The shell temperature and then the air temperature, how did it separates. Okay?
So that difference there is really because of all the heat produced by
the embryo.
So at what point is your heat in your cabinet probably turning off? Is it turning off there around the 6.5, 7 days when? Actually,
in our single stage machine, once the machine, it takes about 6 to 8 hours to warm it up from when the profile starts. And we probably got we got a pre-warm, 80, then to 85, and then it goes to 100.4. It takes about 4 to 6 hours, maybe 6 to 8 hours
Yep.
to recover. Once that heat gets in that, gets in it, absorbs into that egg, then it's pretty well through with the heat.
Wow, that's pretty fast.
Yeah. You see the heat come on maybe just a little bit intermittently, but it don't come on very often. You hardly ever see heat on in the neutral and never in the exotherm because it'd all be cooling.
That would be a problem.
Okay. So again, as the embryo transitions from endothermic to neutral and generates heat, the air temperature surrounding the eggs declines to maintain the shell temperature. As the embryo transition continues from neutral to exothermic and more heat is generated, the air temperature surrounding the eggs declines to maintain the shell temperature. As the embryo again continues the process, and we see it just gets wider and wider to control and to regulate the heat that's generated by today's embryo. Okay, I just put this up here to just show you, this is your actual air temperature taken from that same scenario, that same slide with the shell temperature. Okay, and I put one more thing in there. I put the heat produced. So you see all of the parameters that we talked about at the beginning, the air temperature, the shell temperature, and the embryonic heat produced by the embryos, all how it correlates and how it with one another, how it relates to one another. Just a quick word on multi-stage and what this shows, and you have to pay real close attention because what it is, the set point, total incubation time, average fertility, embryo temperatures, and air temperatures. And if I change the set point, then eventually my temperatures will cool in my egg pack. Usually do that if the fertility goes up,
right?
Or, we might have to extend the total hours.
Right.
Drop it another tenth in the same situation, another tenth to 98.5, and probably in the industry, more people's running the 98.5 in the Jamesway machines than any other set point with the high yield breeds today.
Yeah.
Okay. The goal is chick quality, yielding improved field performance and resulting in profits to the company. That's the goal.
That's it.
Managing embryonic heat in the single stage, the machine does it with the profiles and the setups that you put into the machine. In the multi-stage, you do it with the set point, the monitoring, maintenance, and procedures.
Yeah.
And that's it. Thank y'all very much.
Thank you. A lot of info as usual, guys. So in that top left corner, you have the Q&A button. You guys can go in there and drop any questions you might have for Jerry or myself on this topic. I did have another question about the pilot.
Mm-hmm.
Now, most of our customers are not running all their machines with pilot eggs in them, right?
Yeah.
But are most customers now having a few sets of pilot eggs for diagnosis and for profile management?
That's one of the recommendations that I like to do is tell the customers that we need to, maybe 3 or 4 sets of pilot eggs before we can establish the parameters for their particular situation.
Yeah.
So the pilot is or the shell temperature is a very good way, excellent way. I've learned a lot in working with the pilot on profiling.
Yeah, it's certainly an interesting tool.
Yeah.
And so then you should be reevaluating your profile regularly as well, right?
Well, once you get your profile established and it's working, you just don't have to change it every day but breed changes or fertility. Remember the 3 things: fertility, breed, and what was the other?
Age of flock.
Age of flock.
Age of flock. We have a question from Katie. Katie would like it if you could elaborate a bit on why the shell temperature would be a little bit lower in the exothermic stage than in the neutral and endothermic stage.
Okay, the shell temperature or the air around the egg is movement around the egg, and generally the air movement at that stage of development is at its peak. We turn our fans up to either 90, 95 or 100%, so it's more air going around that egg during that time, and that air circulating has a cooling effect, and that infrared sensor is sensing the surface of the egg, which is a little bit cooler than the inside of the egg.
Right.
Because of the air movement around it. What do you call it? Not wind chill.
Convection.
Yeah, convection.
So the convection effect on that shell is causing the shell to be in exothermic, you said about 3/10
About 3/10
of a degree Fahrenheit cooler than the actual embryo or the actual contents of the egg.
Yeah.
But because that is where your heat is being produced at that point,
right.
So that's your hot center, and the way that heat is being removed from the embryo is through the shell and the air movement or the convection over that shell.
And take that back to the first stage, and it's the same.
And yeah.
Because inside is the same as outside.
Yeah. Yeah, because at that point you don't have that heat center inside. Right. You're actually using the air to warm that embryo.
Yeah, you don't have the heat core or whatever. Yeah.
Yeah. I hope that helps, Katie. I have a question here. James, from Vietnam, you would like a copy of this presentation, and yes, all of our presentations should be made available on the website. And also, thank you for giving us your email. We can send you that presentation right away after the webinar, so that should be there. Any more questions? Just show you guys for a second here the website and the upcoming webinars we have coming. Oops, now I can't see it. Come on over here. Sorry. Maybe some technical difficulties. Okay, well, you all can see that, I'm sure. So April 11th, we will be going over the HatchCom 4 session that we had last time, or that we had missed. Curtis and I will take you through the new HatchCom 4 system. And I believe we may be able to offer you guys a bit of a special on HatchCom 4 during that seminar, only if you tune in. So please do tune in so you can get that. Also, I believe April 25th, it's not up here to register for yet, but we will be having a special edition on our parts website launch. The girls who will be managing that website will be here with Krista and I, and we'll be going over how you guys will be able to use the website. Give you some training on that to sort of ease you into it. And then May 9th, Philip is back again, and we're going to be going over some essential hatchery tools and how to use them. So we should have some live parts to play with and show you guys. So that will be an essential for all your maintenance teams, all your hatchery managers, maybe all your supervisors. So we'd love to have you all out for that. All right, we have a bunch more questions. Tyler is saying the profile you want to follow is that universal between broilers and layers?
Layers require a little bit more heat because of the fact that they're physically smaller, don't produce as much heat.
Yes.
So you do have to have a different profile for layers than you do for broilers, just because of the we don't have a high yield layer.
Right.
The layers are just less heat produced.
Yeah.
Of course, they're high fertilities and things, but yet usually we'll run a little bit warmer.
Are you looking for, if you're looking at eggshell temperature, would that be the same profile? Just your air would be warmer? Like your air profile would be warmer, but you're still looking for that 100.4.
You could actually use the pilot egg at the same say 100.2, 100.3 maybe instead of 100.1, 100.2 for your layers, and you can establish your profile from the data or from the HatchCom data that you have off of the pilot eggs.
Yeah.
And that would get a precise answer, but to answer the questions, it is a difference in the layer and broader profile.
Right, for sure. Another question here, this is from James. He's wondering, should you set the temperature by degrees Celsius or Fahrenheit to give the highest accuracy?
Most accurate is the Fahrenheit because it's more precise scale.
Yes.
So we control all of our incubation equipment with Fahrenheit.
Yeah. So like a 0.1 degrees Fahrenheit is a smaller step than 0.1 degrees Celsius, so that makes it more accurate. Also, all of our equipment is designed around controlling in Fahrenheit, so I think it's actually when you do the conversions inside the software anyways. So whenever you're doing a unit conversion, you end up losing a little bit of accuracy in the rounding. So Fahrenheit is always going to be more precise.
Yeah.
But you can still display in Celsius and read those off in Celsius if that's what you need.
Yeah.
Ronald is asking, in a single stage machine, are you suggesting not to combine young, prime, and old flocks to maintain good eggshell temperature control?
Okay, and single stage, that was single stage,
That
right?
is single stage. Yep.
Single stage incubation is designed for all eggs to be of the same character in one machine. That means that, you know, your fertility and egg size and stuff should all be close to the same. Okay, the same character, not identical, but the same characteristics related to fertility and egg size. If you do, and a lot of people do set prime, young, and old in the machine, and what we suggest doing when you do have prime, young, and old is that you put the larger eggs next to the wall and the smaller eggs next to the ECU.
Right.
That way your airspeed will never slow. It'll always be, you know.
Okay. So what about for multi-stage? Same thing? Should we be combining?
Now, multi-stage is an average. Multi-stage works on average. So what we suggest in multi-stage, in our Jamesway multi-stage, is an average of your flocks in each machine.
Right.
In other words, normally, if you're an integrated poultry company, you have about 20% of your production coming from young, 60% from prime, and 20% from old. So that means in a multi-stage machine, you should have 3 primes, 1 young, and 1 old, you know, and of course your 6th position is going out into your hatchers. So,
Okay.
so we do recommend in multi-stage a mix of eggs,
Okay.
generally.
Generally. So single stage, try not to mix. Multi-stage,
Right.
there's a recommended mix.
Right.
And if you're mixing in single stage, there's a specific way to set those.
Again, the concepts, you know, single stage is precise.
Yeah.
Multi-stage is average.
That's exactly it, right? Any more questions? Anyone? We'll just give you all a minute there. Showed you guys the next set of webinars. Please go ahead and register for those at any time. Of course, you'll get the email reminder. It will be on our LinkedIn and Twitter and Facebook and all that social media stuff. So you can also find the upcoming webinars and everything there. I just want to thank everyone for joining us today. We've had a great turnout. Great to see lots of names from all over the globe, which is super exciting. Yeah, so thank you. And I hope everyone has a great day. It looks like we're about done. Anything you want to say, Jared?
Yeah. Just thank everybody for attending or listening or on this webinar, and if we can help you in any way, just let us know.
That's it. As always, shoot us an email, webinars@jamesway.com. If you have topics you'd like to suggest, if you have questions or follow-up, if you need a copy of the PowerPoint, send that to me. I'm going to be traveling basically right now. I'm leaving. So I may not get to your emails until later on tonight, but when I do arrive at my final destination, I will send you guys the PowerPoints and everything on through. And, you know, you can always email me. I can put you in touch with Jerry if you have any questions. And thank you so much. We're going to shut it down now. Thanks, guys.
Thank you.